Welcome, everyone, to day 2 of activated sludge process control. I'm so glad you're back with us. We are going to get started here at the top of the hour. Welcome back, everyone, to day 2 of the activated sludge process control workshop. I'm so glad that you're back here with us, and we are here for day 2. And we will do a quick review of today's plan, just to kind of refresh your memory and highlight some of the important things for today. My name again is Lori Krings. I am your moderator today, and we have Greg Pearson back with us today as our instructor. Okay, so for today's plan, it's going to look very familiar to you because pretty much it's essentially the same thing. We're going to have polls again today. So keep in mind that if you have any trouble with your Zoom polls being blocked from being able to see them with your pop-up blocker, feel free to put your answers right into the chat. That's totally fine. And we will be recording today again, and we'll be providing that recording when certificates go out. Keep in mind, if you had any questions from yesterday that you would like to get on the list for today's Q&A, please drop that in the chat or put it into the Q&A at the bottom of your Zoom window if you would prefer to be anonymous. That's totally fine. And the biggest point for you to take note of today is if you need a certificate of attendance, at the end of today, action is required for you. So I'm going to be putting a survey link in the chat at the end of today's session. And just please be sure to complete that survey within 24 hours because it will expire. And that is how we get all of your feedback on how you thought things went over these last 2 days. And that is how we verify your attendance for your CECs if you need those. So if you have any questions about that, please let me know. Otherwise, make sure you grab that link when I put it into the chat later on today. Okay, so I'll go ahead and put the slides in the chat here soon, and I'm going to pass it over to Greg. Welcome back, Greg.
Thank you, Lori. Welcome everyone to today's training. We had a good session yesterday, and uh, all of you really went above and beyond to participate as we were going through. You did the calculations along with Daryl on the basic math, and we were covering mostly the food to microorganism ratio yesterday, and just a little overview of what we were talking about. The activated sludge process focuses on what's going on in the aeration basin and the secondary clarifier that collects the biomass and recycles it back into the aerator. So you have biomass and microorganisms going back into the aerator as incoming BOD is coming in, and we wanted to balance the food to the amount of microorganisms to ensure we had complete BOD removal while keeping the bugs healthy, and also to optimize settling. We looked at the sludge volume index and the different factors that can affect settling. Today, we're going to be focusing on the mean cell residence time, which is another important process control formula or test that we can run. We'll also talk a little bit about the role of microorganisms in activated sludge, nutrient removal, and we're going to be talking about some common problems that can occur. So things that happen before the activated sludge process, for example, what happens in the primary clarifier or doesn't happen can affect the process, and also things like control of air and control of the activated sludge flows can affect the treatment process. We had a couple of questions yesterday, good questions that had us thinking, and we're going to address those coming up next. But just as a reminder here, the food to microorganism ratio, we had 2 pounds formulas. It was the pounds per day of BOD coming in divided by the pounds of mixed liquor volatile suspended solids, the biomass that we maintain in the aeration tank. Now, the two questions we had, I did some research, and one of the questions was, can algae or vegetation growth occur in a active SBR, sequencing batch reactor cell, and how could it impact treatment? And I did some research on this, and yes, algae growth can happen in a sequencing batch reactor. A sequencing batch reactor, uh, the characteristics of it are that all of the functions, aeration and settling, and the return flows, it all happens in one tank. And so you have these modes where you have it idle, you're filling it, then you aerate, and then you stop aerating and let it settle. So it all occurs in one tank, and it's a good solution for small systems. It's got a small footprint, but it's a little bit different operation to a continuous flow. And often systems will have at least two of these so that one can be filling while the other is treating, because wastewater never stops coming in from the collection system. But algae growth in an SBR depends on four main factors. The biggest factor is exposure to light. So if you have an uncovered tank, light, algae as a plant, and it will facilitate photosynthesis, and algae can grow. So obviously the solution to that would be to cover the tank. If your wastewater has a significant amount of nitrogen and phosphorus in the wastewater, those would be plant nutrients, it can also facilitate growth. Warmer temperatures and also slower moving water. And you can have slower moving water during the idle and settling periods in an SBR. So algae will grow if you have nutrients and light, and slow moving water. How it can impact treatment, well, first of all, it can increase the total suspended solids, and that could be something that gets increased in the final effluent. It can interfere with nutrient removal. The algae can actually uptake nutrients, then they can die off and release the nutrients back in. And so it's difficult to control that unless you have some kind of a advanced system that could precisely control when the algae is uptaking and releasing those. And it can interfere with settling, and it can cause pH fluctuations. So the biggest effects is it can affect settling and could increase total suspended solids. And some solutions that are offered in the literature, the most effective solution is just to eliminate sunlight, which means you have a covered tank. And there are treatment options. One line of treatment is chemical treatment, like copper sulfate, that like you would treat a lake or reservoir for water treatment. Copper sulfate can knock down algae, but trouble is it could also interfere with some of the microbiological processes. It's not ideal. It would have to be a very light dose. Also, there is ultrasonic algae control. It's often used in lagoons where it's an ultrasonic beam that goes out and it actually stops algae growth. It really works, and it can be used uh, in applications such as settling basins or clarifiers. Um, and just by ensuring you have enough mixing in DO, that usually is enough to prevent algae growth. The trouble with an SBR, you have periods of idle and settling, which would give the algae time. It's not being agitated or aerated in that time. So you'd want to try to optimize those. In other words, you wouldn't want to have your settling and idling times be longer than necessary. You'd want to optimize those. So all those things could be potential solutions. There are studies ongoing to use algae for purposely for enhanced nutrient removal, but those are most of them are kind of experimental. It's a very controlled environment to get the algae to grow and uptake the nutrients and then remove them. And they can even use that for recovering resources as well. So that's the answer that I have for you on that. And the other question was, can you, and Daryl partially answered this yesterday. Can you speak on the historical justification for a 5-day incubation period in the BOD test? And I had kind of wondered that myself. But for some reason never really took the time to look it up. And as Daryl mentioned yesterday, historically it was the time for the wastewater to travel from the Thames River to the ocean. Uh, but there are some other justifications, reasons why this 5-day test occurs. First of all is biological. The organic matter, the biodegradable organic matter, which is the BOD, basically, it is mostly consumed within a 5-day period. That's probably the more easily biodegradable matter. So after 5 days, you have a good idea of what your carbonaceous oxygen demand is. That's another way of saying the oxygen that is needed for bacteria and other microbes to consume the BOD. After 5 days, the majority meaning probably 99.9% of the BOD is gone. When the BOD is gone, it allows for nitrification to occur. So the ammonia in the wastewater, which is not part of BOD, can start consuming oxygen in an accelerated rate. So the 5-day period is it's long enough to get full oxidation of the BOD, but short enough so that the BOD test is not affected by nitrification. Nitrification means converting ammonia to nitrate with nitrifying bacteria, and they use a lot of oxygen. They use more, the oxygen demand for nitrification is higher than that for BOD. So if you had a 10-day test, for example, you would be measuring oxygen demand for nitrification, which which would it would give you a distorted view of how much actual waste you have in the wastewater. So that's what I had for you on those two. And let me just look in the chat to see if there's any further questions related to this. And I see all of your locations, Indiana and Michigan and Virginia. All I'm glad to see that you're sharing your locations there. And we're gonna start off with a couple of polls. We have two polls that we're going to launch here in a row that help us to get to know our audience a little bit better. And so if you'd be so kind as to respond to those. The first one here, um, it asks if you represent a small drinking water or wastewater system. And a small drinking water system means you serve less than 10,000 people, and a small wastewater system means you treat less than 1 million gallons of wastewater per day or something close to that. I appreciate you helping us out with this. This is kind of along the range of demographics, but it helps us as we're moving forward to make sure our training is targeting and serving, I should say, the right uh, what our audience needs to know. And as I mentioned yesterday, as when I saw the engagement of everybody and your math skills, we're going to have to start designing an advanced activated sludge training right away.
We're at 88% on that one, Greg. You want to move on to the second one?
Well, if any of the rest of you are able to respond to the poll, let's give it another minute.
Okay.
Or maybe that's all we're going to get
Okay.
for today. And we have a second poll. And the second poll just asks the population of of your community that your system serves. Well, thank you for participating in those polls. We really appreciate it. And we can see the larger majority here represent systems that serve greater than 10,000 people. And the EPA has kind of a definition that a small system is 10,000 serves 10,000 people or less in for water and wastewater, and a very small system is less than 3,300 or 3,000. But sometimes I wonder if if maybe those definitions should be updated a little bit because if you're serving 11,000 people, you're still a small system, but we really appreciate your participation in that. All right, let's move on here, and we're going to start transitioning into discussing the mean cell residence time. And as we just looked at here, we were talking about the FM ratio. It's the pounds per day of BOD divided by the pounds of biomass in the tank, the MLVSS in the aeration tank. So we're trying to balance the food to the microorganism population. In the MCRT, we're trying to get an answer of how many days the solids are remaining in the system. If you remember, we talked about yesterday, the effluent, the liquid, uh, just travels continuously through the system, through the primary clarifier to the secondary clarifier, to the effluent. It's a continuous path, but the solids remain in the system longer because we're recirculating a portion of the solids in the return activated sludge back to the aeration tank. So we're looking at the total pounds of mixed liquor suspended solids in the system divided by the pounds per day of solids leaving the system. So you notice in that MCRT formula, the pounds will cancel out, leaving only days. So you're going to get an answer in days. And the longer solids remain in the system, the it changes the characteristics of the activated sludge. There's a couple other things to think about, and we'll talk about this more a little bit farther into the presentation. But if you hold your sludge solids a little longer, it gives time for certain types of bacteria, nitrifying bacteria, to grow and develop. If you hold the solids too short of a time, you might not get good nitrification of the ammonia. If you're too short or too long, it can affect settling, and it can also affect the types of microorganisms that are in the activated sludge. If we kind of go over our process again, here's our incoming food and our return activated sludge flow going to the aeration tank. And we're holding a certain concentration of MLS in the aeration tank, the mixed liquor. We're maintaining a certain number of pounds of mixed liquor suspended solids. And we're settling out the biomass in the secondary clarifier, and we're recirculating. Now, that circulation path helps us to maintain the solids in the aeration tank. And then we have the waste activated sludge flow. That's how much we waste. The waste activated sludge flow has the biggest impact, or the main impact, or 99.99% of the impact on how long the solids remain in the system, and also the overall amount of solids that are maintained in the system. So if we increase the waste activated sludge flow, it's going to reduce the total time. Like we might have it's like a detention time. We might be holding our solids for 8 days average before they leave the system. And if we increase the waste activated sludge flow, we might reduce it down from 8 days to 7 days, for example. It also affects the total amount of solids that are in the system. So if you increase the waste activated sludge flow, you might also end up affecting the amount of solids that are in the aeration tank. So everything is kind of connected here. I saw some chats coming in. Let me just take a quick look. Okay. And then, of course, the solids would go to some kind of solids handling. So these two process control calculations, it's not like you would do one or the other. You would do both of them. So the FM ratio is balancing the biosolids you're retaining with the incoming BOD, and the MCRT is determining the amount and age of the biosolids that we're retaining in the system. We're basically trying to get these within the design specifications of the plant. The mean cell residence time here, average time in days that the microorganisms remain in the activated sludge system. And there's our equation, the total pounds of MLSS under aeration. So we're going to have a pounds formula. And then the pounds per day of solids leaving the system. That is mainly due to the waste activated sludge flow. And pounds per day of solids leaving the system, that's another pounds formula. So we're at least going to have 2 pounds formulas to calculate this MCRT. Now, some solids also can leave in the effluent. If you look at an NPDES permit, you might see something like you have a limit of 20 milligrams per liter maximum allowable suspended solids in the effluent. And let's say you're achieving better than that. You have your effluent solids down to 11 milligrams per liter, which is which is probably successful treatment, but still there's some degree of solids leaving. So we can also account for those. So what we're going to do is we're going to do a couple of examples where we just look at the pounds of solids that are in the aeration tank divided by the pounds of solids that are leaving through waste activated sludge. So we're going to do that. That in itself can be a way of process control. The main thing with process control is consistency, doing it the same way each time. And then we're going to do an example, at least one example, where we account for all of the solids. And now that example, where we account for all of the solids, we're going to be looking at the solids in the aeration tank and the clarifier and the solids leaving. We're going to look at the solids leaving through waste activated sludge flows and through the effluent. And that is a more complex, well, not really complex, it's just a more involved calculation. And that would be the type of calculation that you would see on a certification exam. But for process control, you may be able to get by with just looking at the aeration tank volume and the waste activated sludge flows. And so if you look at that MCRT formula, you see the pounds per day of solids leaving the system. That's mostly due to the waste activated sludge flow. So if you want to increase um, the MCRT from say 6 days to 7 days, you would actually decrease the wasting. That would be like a fraction, going from a quarter to a half. A half is larger than a quarter, and of course the opposite is true. If you need to decrease the MCRT, you would increase the wasting. And it makes sense conceptually too, right? You're going to waste more, um, and so the sludge is going to be retained in the system a smaller period of time. So I'm going to do an example here with you. Hope you have your calculators and your scratch pad and pencil or pen close by. Uh, we're going to do a kind of a conceptual problem here. We have a conventional activated sludge plant, and it has a total of 36,000 pounds of mixed liquor suspended solids under aeration. So in the entire system, we have 36,000 pounds. And we know that we are getting rid of 6,000 pounds per day. And so you can probably do this in your head. It's a detention time type of a formula here. We're just looking at the concept. So if 6,000 pounds leaves each day from that 36,000 pounds, how many days is it? And I see a lot of answers here, 6 days, and you're right. And so this is conceptual. The pounds in aeration divided by the pounds per day leaving. I've drawn a little diagram here. So we plug in our numbers. 36,000 divided by 6,000 is 6 days. The pounds cancel out, leaving only days. So this is the simple version of the problem here. And now we're going to get into a problem that's a little more realistic here, but still we're only going to account for the aeration tank volume and the waste activated sludge flow. If you have a small plant and you're not carrying a lot of sludge in your clarifier, let's say you had more than one clarifier and you had significant sludge blankets, this might not be as effective of a process control formula. But if you just have a, a treatment train that has one aeration tank and one clarifier, and you're keeping your sludge blanket below 2 feet, between 1 and 2 feet, you could probably get by with just calculating the aeration tank volume and the waste activated sludge flow for process control. You'd be able to see that if it's increasing or decreasing over time. Um, Once again, for a certification test, you're going to want to include everything, and I'll show you how to do that in a moment here. But I circled something there. It's the waste activated sludge flow. I used Q for flow, is given to us in gallons per minute. We're going to want that to be in million gallons per day. The solids under aeration, we can calculate that with our aeration tank volume. It's 5 million gallons, and our mixed liquor suspended solids, 2,280 milligrams per liter times 8.34. But our waste activated sludge flow, we're going to have to do some conversion there. And here's our equation for MCRT. Well, first of all, we convert the waste activated sludge flow to million gallons per day. And how I'm going to do that, so I'm going to take the 115 gallons per minute and times it by 1,440 minutes in a day to see how many gallons in a day, and then divide that by a million. And I'm going to look in the chat and see if someone can give us the answer in MGD. How do you do this if you don't know your WAS flow or no way to accurately measure this flow? Well, you would need to be able to measure the flow. You would probably, if your plant doesn't have a way to measure the WAS flow, you might need to add a mag meter, which is a magnetic meter, to measure the flow. And the reason we use mag meters is because other types of meters that may come into contact with the wastewater would be would be corroded or clogged by the solids. But you would definitely need some kind of a meter to calculate that flow, and then you would have to do a sludge. You would have to analyze the solids in the sludge by by taking that sludge and filtering it and do an MLS test. So yeah, you wouldn't be able to do it if you didn't know the WAS flow. So I see a couple of you have given the answer to the MGD here, and a couple of you have gone all the way ahead and calculated the number of days. So great job on all of you, and I see some correct answers there. So we have the flow in MGD, 0.1656. I kept some of the extra decimals there. We would probably round this down to 0.17 or round it up to 0.17, but I'm retaining some more of the decimals so that it more closely matches what you might see on your calculator. And so we can use the pounds formula. I'm kind of doing the bottom of the equation first, but use the pounds formula now to determine how many pounds per day are wasted. And now we have our flow, 0.1656 times 8,110 milligrams per liter. That's about a 0.8% sludge solution times 8.3 per pounds. And we have a total of 11,200 pounds per day that's leaving the system. And to determine the pounds under aeration, we have the volume of the aeration tank, the 5 mg times 2,280 milligrams per liter of MLS. That's what we're maintaining in our aeration tank times 8.34. So we have 95,076 pounds under aeration. And we simply do a division to determine the MCRT, mean cell residence time. And some of you have already given the correct answer, but 95,076 divided by 11,200 pounds per day leaving the system gives us a total of 8.5 days. So you're all doing an excellent job. Let me see if there's any questions here before we move on. Oh, Donald, you and Scott, you said 8.49. You're even more specific. Excellent job. We have our first poll here for based on the content here. We have a plant with a zero point 0.5 mg aeration tank, an MLSS concentration of 4,000 milligrams per liter, and the waste flow is 6,500 milligrams per liter with a 0.04 MGD flow. What is the MCRT? And we'll give you enough time to complete this. All right, we'll give it another 30 seconds or so here. Yeah, if you're working on your answer. Okay, we're gonna uh, in the poll, and if you can see the poll, it looks like 82% said 7.69 days. And remember, we're tricky. We might make some of the answers match common mistakes. Let's look at the solution to this here. I've drawn a little diagram here as the aeration tank and the clarifier. And first of all, we're going to look at what is the total pounds of MLSS in the system. And we're just looking at the aeration tank. That's the only information we have. And it's zero point 0.5 mg and it has a concentration of 4,000. So that's a pounds formula. So zero point 0.5 times 4,000 milligrams per liter times 8.34 pounds. I want to look at this question here real quick. Excuse me. So MB is saying that they understand the importance of the calculation, but how can it be applied to a small plant that may not waste daily? That's a good question. It's intermittent wasting. For example, one of my plants is a 0.036 mgd and only gets about 6K of flow daily. And I may go a month without wasting sometimes. When I do waste, I let it thicken overnight in the clarifier with no RAS flow. My waste is sometimes 2% solids. Um, there is a way that seems your particular plant, it's that is a little more extreme version of intermittent wasting. But the um, the um, the flow of waste activated sludge can be continuous. That's the ideal situation for a conventional plant. So, for example, in this one, it has a loss flow of 0.04 mgd, but the if you did intermittent wasting, let's say if you wasted per day, you would still, once per day, say, for example, you would still want to waste the same amount of solids. And of course, you could do times that by 7, and that's how much you would waste in a week. Uh, you're wasting once a month, and I wouldn't want to give you a quick answer off the top of my head for that. But we have some other engineers here at MTU. It's an engineering school that if you wanted to delve into it a little bit farther, if you wanted to optimize that plant, we could probably look at it as it's a unique situation, and we can give you some help on that. I hope that helps. Now, back to our problem here. The pounds of MLS in the system is calculated by taking the volume of our aeration tank and the MLSS that we're holding, zero point 0.5 times 4,000 times 8.34, and we get 16,680 pounds in the aeration tank that we're holding. And how many pounds per day of loss is leaving the system? We have this flow of 0.04, excuse me, times 6,500 milligrams per liter. That's about a 0.65% solution. So it's still kind of thin, but it's going to look dark, times 8.34 pounds per day. So we're wasting this much per day. So if we were going to do intermittent wasting, let's say we were going to waste once per day, we'd want to run the waste activated sludge flow and to long enough to get rid of 2,168.4 pounds. Um, and probably if we were doing intermittent wasting, we probably would do it more often than once per day because the problem is if you hold sludge too long in a clarifier, it can the bugs can become unhealthy, and that you could even get a situation where you have rising sludge or septicity. So a system like was just described, where you're wasting once a month, it sounds like you're taking steps to not allow that to happen. So I'd love to hear more about it uh, offline after the training. I hope you'll send us an email, and would love to know more about that. So we're wasting 2,168.4 pounds a day, and our MCRT is simply a division problem now. 16,680 in the aeration system divided by the 2,168.4 pounds that are leaving, and we get 7.69 days, just like almost all of you calculated. So great job on that. And thank you for the great questions. You're keeping us on our toes thinking here. So our aeration basin and our waste activated sludge are the main components in the MCRT, but you might need to include the secondary clarifier volume to obtain a more true and accurate MCRT, especially if you have a significant sludge blanket. If you have a lot of sludge, if it's the sludge blanket is kept at like 1 foot, uh, you can really just drop it for practical purposes. Um, but if there's a significant amount of solids, you'd want to include it. And I included a link on this slide where it's a good blog um, that you can go to, and you'll have this if you have the slide handout. But it goes through all the different process control formulas. I think you might be a good reference for you to keep. There's also a references sheet that we put together for this training that has activated sludge manuals and process control manuals that goes beyond what we were able to cover in just this class. So here's our MCRT, the pounds under aeration divided by the pounds leaving. Now, if we look at the pounds of solid under aeration and we include the secondary clarifier, that's going to change our formula a little bit. So the pounds of solids under aeration, the solids in the aeration, and the secondary clarifier. And the solids leaving include the solids that are leaving in the effluent, just a little bit of solids, hopefully, plus the solids that are leaving in the waste activated sludge flow. Okay. And so what would that look like if we include all those? Well, here's what the top of the equation looks like. The pounds of solids under aeration, we would simply add the aeration tank volume plus the clarifier volume, the operational volume of the clarifier, and we would use the same mixed liquor suspended uh, solids concentration for both of those. Because in the aeration tank, you have a certain MLSS, and it's all churned up and mixed, and that pours right into the clarifier. Uh, Now, the clarifier does separate the solids from the liquid, but as it goes in there, it has the same MLSS. So all you have to do on the top is add the volume of both of those. On the bottom, the solids leaving, you have two pounds formulas now. You have the pounds per day of the suspended solids leaving as waste sludge, plus the pounds per day of solids leaving in the effluent. Now, the flow of the waste activated sludge that's a waste activated sludge pump flow. That's going to be different than the plant flow. But the pounds per day of solids leaving in the effluent is the plant flow. So if the plant flow is 1 million gallons per day, you would calculate the solids leaving in the effluent using that plant flow. And I'll show you an example here. So you have 3 pounds formulas to calculate this. So I'm going to give you an example here. It's going to get a little bit cluttery on this slide, but I'm just going to show you an example here of how you would do it. So we have a plant flow of 3.25 MGD. So it's a 3.25 million gallon per day plant. And we have some effluent suspended solids that are still in the effluent. uh, 21.2 milligrams per liter of TSS. The aeration tank volume is 1 million gallon. The MLS concentration is 2050. The operational volume of the secondary clarifier is 0.25 mg. And we have the waste activated sludge flow, 0.055 mgd, and the concentration, 7,980 milligrams per liter. Now, let's plug these in to that formula and see what it looks like here. So first of all, on the top, we have the aeration tank volume, which is 1 mgd, plus the clarifier volume, which is 0.25. The MLSS is going to be 2050 for that pounds formula. On the bottom here, for the waste activated sludge solids, we have the waste activated sludge flow 0.055 plus the concentrate times the concentration 7980 times 8.34 plus another pounds formula at the bottom. The effluent is going to be the plant flow, 3.25 mgd times the effluent solids, 21.2. So if we plug all the numbers in, here's what it's going to look like. The tank volume plus the clarifier volume on the top times the MLSS. And on the bottom, we have 2 pounds formulas. You see the pounds formula on the left for the waste activated sludge flow, 0.055 times 7980 times 8.34. We're going to add that to the solids leaving in the effluent, 3.25 times 21.2 times 8.34. Anyone want to take a shot at solving that? Those 3 pounds formulas and doing the division? I see answers coming in. Okay. 5, 5.1, 5.05. Okay, good. Excellent job. I'm going to show first of all the top and the bottom. The top that I calculated came out to 21,371.25 pounds. And the bottom I had 3,660.4 leaving as waste activated sludge. But look how much is leaving in the effluent. I mean, you would think it would be more insignificant than that, but there's 574.2 pounds per day in the effluent of this plant, and these are not extremely. I mean, these figures that we're using is not uncommon. These are not uncommon numbers, but imagine 575 basically pounds of solids going into the receiving waters every day. I mean, after 10 days, there's almost 6,000 pounds of solids going into, say, a river. So if we do the division, 21,371 divided by 4235, I got 5.05 days, which matches a lot of the answers I saw coming in. Great job on that, everyone. Now, the average time for MCRT can range between 5 and 10 days on average. There are plants that can be a little shorter than that, and so there's a lot of variation. Every plant is its wastewater treatment is it's I would say it's almost an art as much as it is a science because each wastewater, the quality of each wastewater plant, the environment, the temperature, even the materials that are being used in the tanks, um, and the aeration and so forth, those all have an effect. And so every plant is a little bit different, but in general, it can range from 5 to 10 days. And you'll typically have a target MCRT that you're trying to achieve. And so conventional activated sludge, it has higher aeration and more simple organisms because we're not holding the sludge as long in a smaller footprint and we're feeding it a little heavier, a little higher FM. If we have extended aeration, then you see an image there on the bottom right of what they call a racetrack. you're feeding it a little lower, so you have a smaller FM, a little bit lower aeration. You're holding your sludge solids for longer. And as we saw yesterday, the length of time holding the sludge and the FM ratio both affect settling. And so in the extended aeration, you're going to have more complex organisms. You're going to start to see protozoa and rotifers in greater numbers. And I'll show you some of those images a little bit. We already have hole two coming up. And this is your chance to respond to kind of a conceptual question. You don't have to calculate the pounds formula this time, and you can almost do it in your head. So we have a target MCRT of 6 days that we're trying to maintain. All right, I want to give about 30 more seconds if you're still working on it to get your answers in. All right, let's take a look at the solution here. Um, Now, this particular plant, 20,100 pounds under aeration and about 4,200 pounds aeration pounds per day leaving the system. I can kind of estimate in my head that we're close to 5 days as an MCRT, and we'd like it to be closer to 6 days. Now, would this be a total disaster if we had five instead of six? Probably not. Um, but as I mentioned yesterday, we might have a trend going on. If we're wasting a little bit too much or a little bit too little, maybe that results in a more significant difference in the future. And Jeff, that's a good question about why use MLSS versus MLVSS. We use the MLVSS in the food to microorganism ratio. It's based on a test. Remember, we filtered the solids, and then we do that. We put the solids in the oven to see how much of it is represents actual biomass, organic material, and that will be a little bit different for every plant. And so we want to know how many microorganisms are there for the food. In the in the overall solids, when we waste with the waste activated sludge flow, that WASP flow, it removes all of the solids. There's no way to selectively remove just the MLVSS, for example. So it's removing all the all of the MLSS. So the only way we would be able to calculate the total solids, um, the age of the total solids would be to use MLSS in that case because the WASP flow there's no way to selectively remove just MLVSS, for example. You know what I mean? So it's a good question. I mean, that's a good thing to think about. Okay. So if we look at the solution here to this problem, our 20,100 pounds divided by the 4,200 pounds per day that are leaving, just a little bit under 5 days, 4.8 days, which is lower than what we want. So because the MCRT is lower, it means the solids aren't retained long enough. So we want to slow down our wasting a little bit. So we decrease the wasting rate. And if you have a very low MCRT, how do you think it could affect treatment? Well, it could be that it results in not having enough microorganisms to consume BOD. And also, microbes might not have enough time to grow and multiply. It could also impede nitrification because these nitrifiers that are in the solids, they need time to grow, and there's just a few of them, so they can be overrun by all these uh, other types of bacteria that are consuming BOD, and so they don't really work well until the BOD is gone anyway in the plant. And once again, this does affect settling. So you want to control the MCRT within that target range because you're trying to optimize the health of your biomass and you're trying to optimize the settleability of your sludge. If you hold it too long, it can you can have sludge bulking or different types of microorganisms. If it's too young, you tend to get microfloc. And here's another way of looking at it. Here, if the sludge is very young, um, compared to very old, it causes problems. If it's very young, you're not going to have sufficient growth and you're going to have very simple organisms. If it's too old, you're going to start getting different types of microorganisms and bacteria die off, which results in poor settling. But right in that healthy area, um, you're going to see, if you look under the microscope, a large amount of stocked silates, for example, and healthy flock starting to develop bacteria that are forming bacterial flock. And you'll see just a couple of rotifers. So that those two healthy columns is where you want to be. You want to see a majority of stock silates and just one or two rotifers. And here's a diagram of the microorganisms that you would see in the uh, very short MCRT. You'll see things like amoeboids and free-swimming silates. Here's what an amoeboid looks like. You'll see stock silates when you're kind of in that sweet spot for activated sludge. And you might see one or two rotifers, but if the sludge is very old, you're going to start seeing a lot more rotifers. That would tell you also by microscopic examination that your sludge is getting too old. And we'll look at a couple of functions here of and characteristics of microbes that are actually in wastewater. First of all, there's protozoa. And these can occur as the wastewater gets a little bit older, and they actually consume bacteria. They're a good sign of healthy wastewater. They're an indicator that you have a good amount of bacteria and that you have healthy conditions in the wastewater. Protozoa, they're free swimming like little animals. And there's different types. There's amoeba and flagellates and xylates. Those are different. Some of them use pseudopodia, which are like false feet. They use their cell wall to walk around. Others use a little like a fin, and some use cilia to move around. Here's a image of a rotifer. They're like little water bears. They're animals that they will go and consume bacteria and other matter, and they're also a good sign that you have healthy wastewater. If you just have one now and then, that will tell you your wastewater is healthy and you're in the right zone. If you have a lot of them, it could indicate you're holding your solids too long. Bacteria is the star of the show in activated sludge. They break down BOD and they aid in flocculation. They form kind of like biofilm to form floc. And there's different types. There's aerobic bacteria that require oxygen. Those are the type that we want to propagate in our activated sludge. They're very efficient at consuming BOD. There is also facultative bacteria that can they can use oxygen, but they can also remove oxygen from compounds like nitrate and sulfate. And then there's filamentous bacteria. There's good and bad parts with filamentous. There's a little bit of filamentous bacteria can be good to help you form a nice, strong flock. It's like if like rebar in cement. It helps to create a little structure for the flock. But if you have too much, if you have low DO or toxicity, you can get too much filamentous bacteria, and then your sludge won't settle well. Then there's nitrifying bacteria. There's nitrosomas that convert ammonia to nitrite, that's halfway. Then nitrobacters that convert the nitrate to nitrate, and they operate best at the end of the aeration tank when most of the BOD is gone. And so you can see a little diagram here of what a flock particle might look like in bacteria, and you have different types of bacteria like filamentous and different organisms that's creating a bacterial flock. And the nitrifying bacteria, there's three steps like we just mentioned, and getting rid of ammonia is very important in wastewater treatment. And so there's two steps. Your ammonia goes to nitrate, and then nitrite, and then nitrate goes to nitrate. So it's a two-step oxidation process that is facilitated by bacteria, nitrifying bacteria. And we want to get rid of ammonia because it's toxic to aquatic organisms. And so you need to have good aeration for nitrification to occur. And here's the chemical reaction. Ammonia can be expressed as NH3, but it can also be expressed as the ion NH4. Now, these nitrifying bacteria are a little more sensitive than the bacteria that consume BOD. So if you have a real low temperatures, a little bit of toxins, if you have too much bacteria, too high a population of bacteria that are consuming BOD, they won't be able to grow and function. And so if you think of the aeration tank, starting at the beginning of the aeration tank, you have a lot of BOD being consumed, and those bacteria are growing and reproducing and consuming the BOD. Near the end of the tank, the BOD is gone, and that gives a little window for those nitrifying bacteria to to grow and perform their function. If you convert ammonia to nitrate, you haven't actually removed nitrogen, but you've converted it from a very toxic form to a less toxic form, and you might uh, still be meeting your permit limit without having to do anything in addition. However, if you had a permit that was being that had a nitrate limit that you were exceeding, you would also need to do denitrification to try to get rid of the nitrate. So here's what nitrification looks like. You're going from ammonia to nitrate, but if you needed to denitrify, you would go from nitrate to nitrogen gas, and that occurs in a anoxic environment. So the nitrification, it's you have a lot of DO, dissolved oxygen. It's an oxygen-rich environment. But denitrification works the opposite way. And the reason it does is because certain types of bacteria, the bacteria that denitrify, they will consume oxygen if you give them oxygen. But if you put them in an environment where the only source of oxygen is for them to break down nitrate, they'll go in and they'll break down that nitrate molecule. They'll take the oxygen from it and they'll take the oxygen and it just leaves the N2 gas. And the N2 gas just bubbles off as gas. And that's how you get rid uh, of nitrogen. And I'll go into that a little bit more here in a moment. But for nitrification, um, you want to have good BOD removal. You're not going to get good nitrification unless you're removing at least 80% of the BOD, so it can start working. The DO needs to be at least 2 milligrams per liter of dissolved oxygen, and it needs to be in a temperature range. The ideal range would be about 77 to 86, but the if it gets too cold, the nitrifying bacteria can stop working, um, and it's hard to get them restarted. And so that's why some plants will use their biogas to heat, or they'll have their facilities kind of in a heated building. And so as the temperature decreases, you get decreased rate of activity. And it might be that your rate of activity decreases, so you're getting less ammonia removal, and maybe you're still meeting your permit. But if you needed to increase the performance, that's one of the things that you could do is keeping the temperature up. Also, you have to be aware that when you're oxidizing ammonia to nitrate, there is hydrogen ions released, and it can affect the pH. There could be a pH drop that can affect treatment. And so in some cases, you have to look at the alkalinity in your wastewater. If you had very low alkalinity for some reason, that could be a barrier or it could be a reason why you're not getting good nitrification. Also, another thing that you can do to improve um, nitrification is to hold the solids longer. We just calculated the MCRT and we had a range there uh, from like 5 to 10 days was the range, the typical range for conventional activated sludge plants. So you might, for your particular plant, you might have a tighter range than that. That's the range of different types of conventional plants, but you might want to be closer to the high end. And the reason is that gives your nitrifying bacteria time to grow and populate. And also you might want to have your FM ratio be a little bit more toward the low end. So if you had a range, so those are things that you could try. Let's say you have your FM ratio and your MCRT set for optimal BOD removal, but you want to improve your nitrification. A little bit lower FM ratio and a little bit higher MCRT might help. So this is showing the equation when ammonia is oxidized. You see it results in nitrate, water, and some hydrogen ions. So that could reduce the pH. And for every 1 milligram per liter of ammonia that's converted, about 7.14 milligrams per liter of alkalinity is required. And this little chart here is the pH versus the nitrification rate. and this is for a particular temperature. So every temperature would be a little bit different. And so you can see the max nitrification rate, it improves as you increase the pH there. And it's reduced as the pH goes down, down at six, a pH of 6, which would be pretty low, but which could occur if you had very low alkalinity as you're nitrifying. But it's only about 12% of the maximum nitrification rate. That doesn't mean you still can't nitrify, it's just slower. But if you have low pH, it could affect. And at 7.5, we're getting about a 70% of the max nitrification rate. So uh, warmer is better, and uh, a pH that is closer to the 7.5 to 8.5 is actually the best. So I'm going to give you an example here. I'm not sure why that is doing that, but we have a wastewater plant that has a raw wastewater that has 150 milligrams per liter of alkalinity, and we also have 15 milligrams per liter of ammonia. So let's calculate how much alkalinity would be used up by complete nitrification of the ammonia and how much alkalinity will be left over. So for some reason, some of these numbers are showing up here, but ahead of the other ones. But here's the alkalinity that is used up by nitrification. We take the 15 milligrams per liter of ammonia, and remember we said about 7.14 parts of alkalinity is used up for every part of ammonia. So 15 times 7.14 gives us 107.1 milligrams per liter of alkalinity, and we're measuring alkalinity as equivalent to calcium carbonate. So we would lose 107 uh, 0.1 milligrams per liter. We started out with 150. So uh, the alkalinity remaining here, we take that original 150 milligrams per liter and subtract the 107 that's used up, and we have 43 milligrams per liter of alkalinity is remaining, which at least we have some alkalinity remaining, but it is a little bit low. And in general, we'd like to see at least 50 milligrams per liter of alkalinity remaining. So in some cases, we may need to add some kind of adjustment, such as lime, to improve nitrification. So for nitrification here, we need to have adequate temperature, enough alkalinity, a pH ideally above 6.8, and we want to have sufficient DO because nitrification uses a lot of DO. And we want to have enough solids. We want to hold our solids in a great enough abundance and long enough to promote the growth of those bacteria. And they're particularly sensitive to toxins. So at some point, as we go from left to right in our aeration tank, we're going to get to a point where the nitrifying bacteria are going to function. They're going to start to function better and better at the point where at least 80% of the BOD is removed. And so we have here at the end of the tank here, before we discharge into the secondary clarifier, we have either very low or no BOD left and very low or no ammonia left. And uh, we don't have DO if we've timed it right, but we do have nitric oxide, sorry, a nitrate, uh, NO3 in the wastewater. I see it's about 2:16 now. We're going to be taking a break in about 14 minutes. And then we have our activated sludge microorganisms. We want to keep them healthy, so we're not going to keep them in the clarifier for a long period of time. And we want to focus on optimizing these nitrifying bacteria. They grow at a slower rate, and they're very sensitive to things like pH and temperature and toxins. So just like we said, maintain a sufficient sludge age, use a higher biomass and a lower FM ratio, control the pH and maintain at least 2 milligrams per liter of oxygen, and try to prevent toxins from entering the system. Now, denitrification, remember we at the end of that tank we were left with nitrate but no DO, and that's exactly what denitrification requires. And because the Pseudomonas bacteria are going to be responsible to go and take the oxygen from the nitrates, and that when the oxygen is gone, the nitrate is just nitrogen gas, which bubbles away. And these Pseudomonas, they're facultative. They can use oxygen, but they prefer oxygen, I should say, but they can use nitrate. So they biologically reduce the nitrate to nitrogen gas, and they have special enzymes where they strip the oxygen molecules from nitrate. Now, the trick is that they require some kind of a BOD or a carbon source. And why is that? It's because they need to eat. If they didn't have something to eat, they wouldn't need oxygen. It's just like in BOD, the bacteria see some BOD there to eat, and they say, "I'm going to go eat that piece of BOD," but they need oxygen to accomplish it. The same with these denitrifying bacteria. They see a nice piece of carbon or BOD, and they need oxygen, so they strip it from the nitrogen, the nitrate. The problem is, by the time we get to the end of the aeration tank, the BOD is gone. So there's nothing there for them to eat. So what reason do they have to strip oxygen from the nitrate? So if we go uh, look at our plant here, and we get to the end right here of our aeration tank, we have low BOD or no BOD, and we don't have any ammonia left, and it's converted to nitrates. But if we were to place an anoxic chamber here at the end, what would be the problem with that? The wastewater flows into here. What would be the problem? What would be the problem if it just flowed straight into the anoxic tank from there? Well, the problem is, let me see the chat here. No BOD left. Yeah, there's nothing for them to eat, which means they'd have no reason to strip that oxygen. So, how can we solve this? There's a couple different ways that we can solve it. One is to place the anoxic tank at the beginning. So the incoming wastewater flows through the anoxic and then into the aerobic. By the time we get to the end of the aerobic aeration tank, we have the BODs gone and we have nitrates. We recycle it back to the beginning where there is BOD. So it's a continuous cycle here. So that's one way. And this is a biological process that where you're using the naturally occurring BOD. The denitrifying bacteria now can consume the BOD and use nitrate, and then the gas will bubble off. Another way to do it is to use an external carbon source. So you get to the end of your aeration tank, and you have low BOD and low ammonia, and you can use an anoxic tank um, where you add an external carbon source, such as methanol. So you don't have to use BOD in this situation. You can use an external carbon source, and there's lots of different external carbon sources that can be used. Methanol is the most common. It's effective and useful, but adds it does add some additional expense. There's various plant arrangements here. This particular one here. Um, is the same as we just looked at. The BOD is gone at the end of the aeration tank, and we're recycling it back to the anoxic period. And this one has an anaerobic step at the beginning. That is for phosphorus removal, and we'll talk about that in a moment. With a sequencing batch reactor, a lot of times we can have some flexibility of control over a sequencing batch reactor because it has a series of steps. It's just like an aeration tank, but it also acts as a clarifier. And you see the five steps of a sequencing batch reactor. You have the fill, and then you react by turning on the air. Then you settle it by turning off the air, and you have some decanting where you're pulling off the effluent and some of the waste activated sludge solids, and then it sits idle and fills again. So by controlling the length of time of each of these cycles, you can actually control also the or create the conditions for nitrification and even denitrification to occur. So, for example, if you had an extended time where you left the air off, um, you could create potentially an anoxic environment that would allow denitrification or just alternating between air on and air off cycles. And there are some case studies on this, and it should be in your reference sheet. In a extended aeration activated sludge plant, you have a little racetrack here where there's a larger amount of solids being retained, and they have surface aerators, and they're moving around kind of what they call a racetrack. And you still have a secondary clarifier and a return activated sludge flow. These aerators can be turned on or off. Uh, for example, that aerator on the top would be turned off periodically. It could create an anoxic zone right in the same basin. So you're aerating and you're nitrifying the bacteria. Then you have a anoxic zone that you maintain, and then you have denitrification, and the nitrogen can bubble away. So those are modifications to existing plants that can help. And denitrification is a little more forgiving than nitrification. It occurs across a wider range of temperatures and pHs. So it's less sensitive, but you have to have enough carbon or BOD for it to have something to eat. And it actually adds alkalinity back because it releases hydroxide ions. And now we're ready for pole three. And after pole three, we'll be taking a break. How are you all enjoying the training so far? Are you following along? Let me look in the chat to see if there's any questions. Lori, I see a question came in from Jacob. He can't see the poll box? Is there anything that we can do or he can do to see that?
Yeah, it's actually a common problem. If you can't see the poll window, it could be you have pop-ups blocked for that Zoom setting. So if you can't quite fix that, go ahead and put your answer in the chat.
We'll give another 30 seconds here to get your answer in, and then I'll show you the solution to this problem. Um, and then we're going to be taking a break. I want to know uh, if a 5 minute break is going to be sufficient for everyone to stretch and get a warm beverage, or if you'd like or need 10 minutes, let us know in the chat, and we'll make it a 10-minute break if you need 10 minutes. Okay, we got a couple of people that are say they need 10, so we'll have a 10-minute break. Let's in the poll here, and I'll show you the solution, and then we're going to have a 10-minute break. Oh, you already started the timer?
Nope, I didn't start it.
Okay,
It
okay.
started itself, so
Oh,
we're not
oh, okay.
going yet.
Because I could have done it when we come back too, but basically the solution is easy to show. We had 20 milligrams per liter of ammonia, and we estimate that it takes about 7.14 parts of alkalinity for every milligram per liter of ammonia. So we just take the 20 times 7.4 to estimate uh, that it's going to use up 142.8 milligrams per liter of alkalinity. And we have to do a little subtraction next. We started out with 195 milligrams per liter, and we used up 142.8, and it left us with 52.2. And so you guys did a great job on that, and we'll see you in 10 minutes. Thank you for all your participation today.
Okay, so I do have the timer going for the break. You should be able to see it at the top of your Zoom window, and we'll see you back here shortly after the 10 minutes. Have a good break. Welcome back, everyone. I hope you had a good break. We are going to get started again.
Okay, welcome back, everyone. Thank you, Lori. Um, we just got through talking about um, nutrient removal, specifically nitrification and denitrification. And while we're talking about nutrient removal, let's touch on biological and non-biological phosphorus removal as well. Um, so for biological phosphorus removal, we actually need an anaerobic zone. And we have to keep it anaerobic for long enough to be effective, but not so long that it actually goes septic. They call it uh, fermentation. And what's going on in an anaerobic zone is there's no source of oxygen in an anaerobic zone. There's no DO and there's no nitrate either. Nowhere for bacteria to get oxygen. And what happens in the anaerobic zone is that certain organisms that are able to accumulate phosphorus, they're able to grow and thrive and become energized in this anaerobic zone. It prepares them to uptake phosphorus, and they will do that once they go into the aerobic zone. They'll uptake phosphorus. So the phosphorus accumulating organisms, PAOs is short for phosphorus accumulating organisms. They grow and consume nutrients in the anaerobic zone environment. And then once they flow to an aerobic zone where you have plenty of DO, they actually uptake uh, phosphorus. And then once they accumulate the phosphorus, when you remove sludge, you're also removing phosphorus. It's biological phosphorus removal. As you can imagine, in an activated sludge plant, you're recycling some sludge back to the beginning too. So it's like you're going to be removing a portion all the time instead of 100% of the phosphorus. But the idea is to knock the phosphorus down uh, below your permit limit. There's lots of different permit limits for phosphorus. There's some plants that need to remove phosphorus down to a 1 milligram per liter level. Other plants in certain places are required to get phosphorus down to a zero point 0.1 milligram per liter level. And most likely, biological phosphorus removal is not going to be possible, um, a possible alternative for a very low removal, just because of that reason that I said, because you're recycling all the time and you're depending on anaerobic and an aerobic environment to accomplish this. Uh, but it can work. It's just not going to probably be effective to get you to a really low. And there's a case study in EPA about the Assabet River. I believe it's in Massachusetts, I think. I'm not exactly sure if I'm not correct on that or not, but this particular river was really impeded by phosphorus, and there was 4 plants that they did a little case study on that all chose different mechanisms to get the phosphorus levels down below at or below zero point 0.1 milligram per liter, and they all 4 of them used a non-biological process where it was like tertiary treatment where they added enhanced settling and filtration using chemicals. So here's the steps of biological phosphorus removal. You have this anaerobic, there's no oxygen at all, and the phosphorus accumulating organisms are thriving and growing, and then they're introduced to an aerobic environment, and these phosphorus accumulating organisms uptake phosphorus, and then they're settled in the secondary clarifier, and a portion is removed through waste activated sludge flows. Sorry, I skipped a little bit too fast there. So that's the basic process for biological phosphorus removal. If you were trying to remove both phosphorus and nitrogen, now remember to remove nitrogen, you have you have the nitrification of ammonia, and you've converted ammonia to nitrate, but you haven't removed it yet. So to remove nitrogen, you have to have nitrification and denitrification. So you see there's three different environments in this diagram. There's the anaerobic basin. There's no oxygen source at all. That is to prepare the phosphorus accumulating organisms. And then you have the anoxic and the aerobic environment here. You have in the aerobic portion, you have three things going on. BOD is being consumed, ammonia is being nitrified to nitrate, and that nitrate uh, is recycled back to the anoxic environment where you have denitrification. And that nitrogen is bubbling off in the form of nitrogen gas. But in the aerobic environment, you also have phosphorus uptake by the phosphorus accumulating organisms. And you want to have your DO be at least 2 milligrams per liter, and the effective range is between about 2 and 4 milligrams per liter. You might see some improved nitro nitrification and improved phosphorus uptake if you increase the DO a little bit. But once you get to, in general, once you get up to about 4 milligram per liter of oxygen, if you go above that, you're probably just wasting energy. So you'd be using more energy than than the benefit you would get out of that. And the biomass that settles in the secondary clarifier includes some uh, organisms with phosphorus, and a portion of those are wasted with the sludge. Oxidation ditch can also be modified to remove both nitrogen and phosphorus. As we saw before, we can create an anoxic zone by alternating one of the aerators on and off. And there was one plant that actually uh, put a oxygen sensor at a certain point in the oxidation ditch, and they operated their mechanical aerator with VFD, which is a variable, allows you to run your your motor at a variable speed. So they were able to run the aerator at the right speed and at the right time and duration, just to maintain enough oxygen so it would run out just before the anoxic zone. So they had a sensor and a VFD and a SCADA system that did this. And this was just a couple operators, and they decided to do some experimentation to try to make their plant meet their nutrient removal limits. And they were going to have to spend about $6 million, which the community didn't have. It was just a small little community. And these operators found a way to make their oxidation ditch into a nutrient removal plant just by doing some of these adjustments. Now, if you wanted to adjust um, or modify a oxidation ditch to just remove phosphorus, you could create an anaerobic zone at the influent where there's no oxygen to prepare the phosphorus accumulating organisms before it enters the aerobic zone, the oxidation ditch. And in the oxidation ditch, you'd be removing BOD and oxidizing ammonia, and you'd be having the uptake of phosphorus by the phosphorus accumulating organisms. So just by adding that one zone. If you wanted to remove both phosphorus and nitrogen, you could create uh, an anaerobic zone, and you could create an anoxic zone. And the anoxic zone, remember, you'd be recycling um, basically back into that zone. So you'd be um, running out of oxygen just before it re-enters that anoxic zone. And you wouldn't be recycling back into the anaerobic zone, it would pass through the anaerobic zone as it enters. And then you'd be able to remove the BOD, oxidize ammonia to nitrate, and have phosphorus uptake in the oxidized or the aerated portion. So at the end of the racetrack, you'd have ideally have your dissolved oxygen has been used up, but you have nitrates before as it enters the anoxic zone, the yellow portion. And here's an actual a aerial photo of a plant in Great Bend, Kansas, where the operators uh, modified. And if you look closely at they had two racetracks side by side there. If you look closely at the bottom one, you can see a portion of that has active aeration going on. You can see that there's some dark churning. And as it rounds the corner, you can see that the aerator is off. So they're creating that anoxic zone. And you can also see on the left-hand side where that little dot is, little laser pointer dot, they've also created a anaerobic zone. So they're actually doing this by modifying the plant. And so they saved their community a significant amount of money by modifying the plant. And they did some experimentation and they added a SCADA system um, and an oxygen sensor so they could closely um, calibrate the nitrogen or the nitrate recycle zone. In an activated sludge plant, a conventional plant, it could be modified something like this, where you'd have an anaerobic zone where the wastewater first flows through, and then an anoxic zone, and then the oxygen-rich zone where you're it's like a regular aeration tank, and you have that nitrate recycle flow is going from the oxidized to the anoxic tank. So there's a continual recycling there that goes on. So you'd be removing phosphorus and nitrogen biologically, and the nitrogen gas would bubble into the atmosphere. And the phosphorus would be removed as a portion of the waste activated sludge. And here's a different orientation here, where you see that in a diagram model here, the the anaerobic followed by the anoxic and the aerobic. In this particular plant, they had a optional additional anoxic tank where you could add an external carbon source for polishing. So it's kind of an uh, AO type of plant, and they finish with another aerobic session. So they're just optimizing the nutrient removal, especially for nitrogen. And with the sequencing batch reactor again, um, you could create an anaerobic zone by having an extended period of air off at the fill cycle. And you could rotate between the react and air off, the air on and air off period to create an aerobic and then an anoxic zone. And you want to it would take some experimentation, but you'd have to experiment it with it if you wanted to do this, but uh, you would start with longer and longer air off cycles until you are getting the correct environment to denitrify and to create that anaerobic zone without going septic. And you can use process control in the form of a ORP probe, an oxidation reduction potential probe. We're going to go to pole 4 now, and I'll show you some more of this stuff here. And this poll is just asking what environmental elements are necessary for denitrification to take place.
Greg, do you have a slide with the poll question on it for those people who can't see the poll window? Thank you.
All right, let's in a couple seconds here, 15 seconds, we're gonna end the poll here. We have your answer, Nicholas. Thank you. All right, let's end the poll. And 84% of you said it needs to be anoxic with the presence of nitrates and a carbon source, and that is correct. The denitrifying bacteria needs some kind of source of food to eat, which is the carbon source. And nitrates. So the denitrification, uh, you have special bacteria that will strip the oxygen from nitrate, and it'll leave just nitrogen gas. And there's basically three different types of environments here. Aerobic, we're looking at it contains dissolved oxygen at a level of probably 2 to 3 milligrams per liter, ideally. I mean, you can get by with 1.5 milligrams per liter. The trouble is that for BOD removal, at least, the trouble is how well is it mixed? You might have, the mixing in a tank won't ever be 100% perfect. You'll have some spots that'll be a little bit lower. So if you have a little bit higher, like around 2, it can help you. But you don't want to go to the point where you're just wasting energy. But so aerobic has oxygen, and what's going on there is BOD removal, ammonia oxidation, and phosphorus accumulating organisms are uptaking phosphorus. In anoxic, it has nitrate but no DO. So denitrifying microorganisms or bacteria, I should say, can strip oxygen from the nitrate, but it requires a source of carbon. BOD is a any organic material is carbon based, or you can just add a source of carbon. And anaerobic, there's no source of oxygen at all, and we use this to make sure that we can energize and grow our phosphorus accumulating organisms. And it does require some BOD. Typically, the raw influent wastewater is what we're using. Now, we can measure these environments with an ORP probe, an oxidation reduction potential probe. So basically, a positive ORP value is an oxidizing environment, while a negative is reducing. So um, we can look at each environment and what the measurement would be. For anaerobic, we're usually looking at somewhere around a negative 200 millivolts, and aerobic is about a positive 150 millivolts, and the anoxic is somewhere around a negative 100 millivolt um, in general. So this could be very useful if you were, say, you had a SBR or an oxidation ditch or a tank that you're trying to modify to optimize organic methods to remove nitrogen and phosphorus. You could you could measure with an ORP to know when you're hitting the right environment, and then of course some timing mechanism to know how long you're holding uh, the wastewater in that environment. Those would both be important elements to know. This particular one, we can see a 217 millivolts. Looks like it's a oxygen-rich environment. Now, for non-biological phosphorus removal, this is usually tertiary treatment. We're using some kind of chemicals um, to cause the solids in the water to clump together and to settle out. So it's chemical treatment, and then you're using settling and filtration. And here is the link to that particular study I was telling you about. You'll have this slide, but the six municipalities, one watershed, the Assabet River watershed in Massachusetts, and this river was impacted by phosphorus problems. And they each one of these utilities, there was four different utilities that served these six municipalities, and they all chose slightly different methods. And so it's an interesting case study, and some of the reasons that they chose the methods were based on the life cycle, which includes the initial cost and then the cost to run them. Like some of them were going to have to increase their chemical usage and increase their electrical usage, while other ones minimized the operational cost and maybe their construction cost was a little bit more, and they had to look at the impacts on also labor and footprint. Some of them had plenty of area to build, and some of them didn't have much area to build. So all those factors were included, and then the actual treatment source or treatment process was also discussed. Excuse me. So chemical precipitation of phosphorus, basically you were adding chemical coagulants to create larger flocks, which can be more easily settled or filtered. So in this diagram on the left, you can see they're adding coagulant and mixing it, uh, gently mixing it to flocculate to cause larger particles, and then allowing it to settle. So one way would be to just to modify the existing plant to convert the primary and the secondary clarifier into optimized settling tanks. So you notice here on the right image, they have some chemical addition of some coagulants that are going to both the primary clarifier and the secondary clarifier that's going to optimize solid settling in both of those tanks. So you can optimize the phosphorus removal just by modifying the plant. A tertiary solution would be some kind of a process that's added on or after the secondary effluent. The water is coming in, and you have the treated water, the effluent from the secondary clarifier. Uh, you add chemicals to that that cause flocculation, where you can settle out the sludge or pass it through a filter to get um, more treatment, more optimized phosphorus removal at the end of the tank. So that's an example of tertiary treatment for that. Now we're going to talk about some common things that can affect activated sludge. And so some of the things that can happen are before the activated sludge process. Like, for example, if you have collection system problems, such INI. INI stands for inflow and infiltration. You know, those are sources of extra water that are coming into the collection system that are either groundwater or rainwater, and it can overload and even wash out the system. So you have this massive amount of water, and it doesn't have the concentration of BOD in it. And this can happen whenever there's a rain event, for example. And you have this massive amount of extra water coming into the system, which can cause problems. You can also have toxicity. One system that we were working with, they had a fairly small town, but they also served two state facilities that they used harsh cleaning chemicals that were affecting their nitrifiers in their in their in their uh, in their treatment process. So toxicity, and also if you have a slow moving collection system, you might have a more ammonia or more, so the wastewater arrives in its septic already. And so that could cause problems with rising sludge and more difficulty trying to remove all that ammonia. You can also have problems at the headworks. At the headworks of a plant, you're trying to remove grit, for example, um, and screen out things like rags and so forth. That could also cause problems. Grit could cause your sludge removal equipment and your clarifiers to wear out faster. So you're not getting good sludge removal, and that can cause problems in your activated sludge process because now you have sludge that's remaining in the primary or the secondary clarifier, and it can cause problems like rising sludge um, in the tanks. Primary clarifier problems could occur if you don't have good sludge removal, for one, or if it's not designed that uh, in the right way to give you the detention time you need. In the activated sludge process, you could have aeration tank problems, like you have a broken aerator, for example, or it's not large enough. You're not getting enough time for BOD removal. In the secondary clarifier, you could have also design issues or inefficient sludge removal. So those are some of the common things that can occur. In general, uh, our process control parameters, we want to maintain the correct FM ratio and MCRT as close to the target as possible. And we want to have a stable mixed liquor suspended solids. So generally something 2,000 to 2,500 milligrams per liter of solids concentration for many plants might be the sweet spot. Um, we want to maintain a sludge blanket that's the right depth, and we want the DO to be sufficient, and we want to ensure the conditions for adequate nitrification. In other words, our sludge age is long enough. We're consuming the BOD before it reaches the end of the tank, and we're not having any extremes in pH or temperature or toxicity. So one of the ways that you can always conduct a process control check is by doing a removal efficiency equation. And you can do this with BOD or TSS or ammonia, but the influent concentration minus the effluent concentration divided by the influent will give you the removal efficiency. And I'll show you an example here. If we had 325 milligrams per liter of BOD coming in, and the effluent BOD is 19. If we plug those numbers in, 325 minus 19 divided by 325, if we convert it to a percent, we would get 0.915 or about 94% removal efficiency. And that's something that you could compare week to week or month to month um, to look for trends and see what your overall efficiency is, especially after you make adjustments to the process. So in the collection system, things that can happen if you have I&I, you can actually wash out your microorganism population. And it can dilute the wastewater and kind of starve the microbes, make them unhealthy. And of course, all your equipment is going to be working harder, and you're not going to have that time to have sufficient nutrient removal or BOD removal. Um, if you have a collection system that is slowed, it'll increase ammonia and septicity and any kind of toxic substances. Uh, and this is a little short list of some different types of common toxins that affect wastewater plants. Because, whoops, I'm sorry. All of these factors can I'm sorry, can affect the bacteria, the microorganisms that are trying to work in the activated sludge process. Heavy metals, any chemical solvents, uh, detergents, biocides, pesticides, or high and low pH. And these types of things will enter the collection system, especially if you have industrial facilities that are discharging into your system. And so the way to handle that often is to work with the dischargers and possibly ensure that they're adhering to their discharge permits themselves. You can also end up with an increase in ammonia in the effluent. So all of a sudden you were meeting your ammonia standard, and all of a sudden you see it start to creep up, or you're no longer meeting it. What has happened? Well, some of the common causes are also with toxicity because the nitrifying bacteria are very sensitive. They're also sensitive to temperature, extremes in pH. If you're not getting good BOD removal, uh, for some reason, that could affect uh, because you need to remove the BOD at least down to 80% before you get good nitrification. If you're not holding enough solids, the if you just to think in terms of a visual example, imagine if you had 1,000 white marbles and one blue marble. That's a similar situation to what's occurring with the proportion of nitrifying bacteria to the bacteria that consume BOD. There's just a few of them, so you want to do everything you can to nurture the population. And so by holding more solids and holding them a little bit longer, it can help the nitrifying and bacteria to accumulate. And also, they need plenty of uh, DO to oxidize the ammonia to nitrate. For process control, one of the main things you want to measure for nitrification is DO. You want it to be at least 2 in most cases. And you can also, even though your compliance tests need to be official lab tests, for process control, you can use a simple fish aquarium test kit for process control. Uh, and you can look at the ammonia before and after, and as you make adjustments to, for example, DO, for example, or MCRT, you can look at the effects throughout the system before and after and in the process. So while your DO needs to be at least 2 milligrams per liter in oxidation for denitrification in that anoxic environment, you want it to be at least less than 0.3 milligram per liter of DO. You're going from the aeration tank, recycling back to that anoxic. So you're carrying some oxygen with you. But as long as it is less than 0.3 milligram per liter, you're still going to be able to have an effective anoxic zone. And you also want to make sure your pH is stable. And remember that equation that to estimate the loss in alkalinity and the remaining alkalinity, you'd like that remaining alkalinity to be at least 50 milligrams per liter. And once again, a little higher on the MCRT range and a little bit lower on the FM ratio. Oops, sorry. Now, in our clarifiers, the primary clarifier comes before the activated sludge process. So some typical problems is that we don't have enough settling time, um, or we have some sludge that is retained in the primary clarifier where we're not getting complete sludge removal. If you look at the bottom here, for this rectangular clarifier, we have a little chain drive. And on that chain at the bottom, there's some little sludge plows or removal mechanisms that chain needs to be adjusted periodically, and eventually those sludge scrapers are going to have to be replaced at some point. So if you're not getting good sludge removal, you can end up having rising sludge and problems with septicity and possibly solids from the primary clarifier entering into the process when they should be removed. So this is an example of the preliminary steps causing problems with later steps. Now, if you have a primary clarifier, it's fairly simple, but there's some things that are going on that that need to be done thoroughly to prevent problems downstream. So you have scum removal uh, processes. The influent needs to be free of grit and screenings, and the primary sludge needs to be removed effectively. And here's an example of a scum baffle here. You see that arm that's going along and it's pushing that sludge to a hopper. And on the right-hand side, you can see the little scum baffle at the effluent weir. So it's keeping the scum out of the effluent and it's raking it to a a scum hopper. And in the sludge removal equipment, you see some of the basic maintenance things would be replacing or adjusting the sludge scrapers, just simple lubricant and adjustment of any kind of mechanical alignment, or in the case of the rectangular clarifier, that adjusting the change. So those are important things that, if not done, they can cause downstream problems. And here's a scraper arm. You can see, you look kind of at a little bit more closely at the nearer the bottom of that picture, you can see those scrapers moving the sludge along. And at the bottom there will often be some adjustable squeegees that can wear out, and periodically you have to drain down the clarifiers and check the adjustment and the integrity of the scrapers. There also can be ways to improve the solids removal by using a DAP unit. Um, Basically, it's dissolved air that's bubbled into the wastewater, and it can help things like fats, oils, and greases float to the top more easily. And if you see those angled lines in that DAP unit, those are little they call them lamella plates that they facilitate the settlable particles to settle more rapidly. And so this can be used as part of the pre-treatment process before it enters the primary clarifier, but it can also be as a final post-treatment to help to thicken the waste activated sludge. So there's a couple places where they use these, but as a preliminary treatment, it helps to facilitate better removal of some of these things. And you can see an actual image of one, and you can see those lamella plates kind of down in the middle of the process, and at the top you can see the equipment to remove the scum that's floated to the top. So in general, primary clarifier should be removing about between 40 and 60% of the total suspended solids, and you could test for that. You could test before and after. It should be removing 20 to 50% of the BOD, and you could do a BOD test before and after the primary clarifier to see how well um, the primary clarifier is working. And just remember that if you have I&I, heavier flows during the wet season, it can hydraulically overload these clarifiers. Low temperatures can affect them, and different kinds of solids can impede the solvings. For detention time, typically it's 2 to 3 hours. And we have a couple of different ways to monitor how well our tanks are designed. There's weir overflow rate, 10 to 20,000 gallons per day per linear foot of weir. And then there's surface settling rate, which is also called the overflow rate. It's the flow divided by area. And the purpose for that is to make sure that particles have enough time to settle before they reach the effluent trough. And that should be somewhere between 300 to 1,200 gallons per day. So I'm going to show you an example here. We have a primary clarifier, and it has a certain diameter. It is 65-foot diameter, and it has a depth of 12 feet, and the plant flow is 1,900 gallons per minute. What is the detention time in hours? And for the sake of time, I'm going to show you the solution for this one here. The detention time, as Daryl showed us yesterday, is volume divided by flow. So we're going to calculate the volume using the diameter and the depth here. And I'm using d squared times 0.785 times the height to get cubic feet, then multiplying by 7.48 gallons per cubic foot. So 65 times 65, you can do this on your calculator with me. We're running out of time here, so I'm going to just keep moving, but I want you to try this in your calculator. 65 times 65 times 0.785 times 12 gives me about 300,000 gallons. 297,700 gallons is the volume of this tank. And if I divide by the flow of 1,900 gallons a minute, the gallons will cancel and it'll leave us only minutes, 156.7 minutes. But we want our answer in hours. So I'm going to divide this by 60 minutes per hour. And I get 2.6 hours. And we wanted our detention time to be between 2 and 3 hours. And we're right in that ballpark. Now, the weir overflow rate is important uh, to make sure we have enough time for particles to settle and um, and not create any excessive current velocities near the effluent. We want it to be a nice, quiet, the water should be almost standing still in a clarifier. So here we have the same clarifier. It has a diameter of 65 feet and a flow of 1,900 gallons a minute. And what is the weir overflow rate in gallons per day now per foot of weir? Now, the weir in a circular clarifier is the circumference of the circle because the weir goes all the way around the perimeter of that circle. So we're going to need to calculate how long that weir is. Now, that's the circumference of a circle, and the circumference is pi times the diameter. So if we take 3.14 times 65 feet, we'll get pretty close to the length of the weir. If you use the symbol pi, you'll get a slightly different answer because it has more decimals. But the length of this weir is 204 feet. So if we look at the formula at the top, the flow in gallons per day divided by the length uh, of the weir in feet. Now our flow is given to us as 1,900 gallons a minute. I'm going to multiply that by 1,440 minutes in a day, and I get a total amount of flow of 2,736,000 gallons per day. If I just simply divide that by the 204 feet of weir, I get 13,412 gallons per day per foot. And the range that we were looking for was somewhere between 10,000 and 20,000 gallons per day per foot. And we're right in the ballpark there. If it was faster, it would mean that we're creating velocity currents that could be carrying solids into the effluent. And the final one that we can calculate is the overflow rate. And this has to do with the ability of the wastewater to settle correctly. So in this one here, it's the same diameter, same flow, but what is the overflow rate in gallons per day per square foot? And so the flow We do the same calculation, 1,900 gallons a minute times 1,440 minutes in a day, and we get that same flow, 2,736,000 gallons per day. And then right here, we did the area, 65 diameter squared times 0.785 is the area. And that, I'm sorry, that is the area of this tank is 3,316.6 square feet. So if we take the flow and divide it by the area, we get 825 gallons per day per square foot. And we were looking for a range between 300 and 1,200 gallons per day per square foot. That should be foot with a little squared on it. But you see, we're right in the ballpark. If we were above or below that, we could have that would give us a clue of if we were having problems in our plant. Because over time, let's say you have a clarifier and activated sludge system that's built in 1985, and since then your town has doubled in size. What would happen to, well, you'd be using a lot more capacity of your system. And the clarifier could be the primary or the secondary clarifier could be the thing that gets impacted if we are loading it beyond. You can also um, look at the range of, I'm sorry, of operation for a secondary clarifier, and it's a little bit different. The detention time is the same, 2 to 3 hours. The weir overflow rate is a little bit lower. Instead of 10 to 20, it's 5,000 to 15,000. You want it to be especially gentle in the secondary clarifier because you're trying to produce effluent water for compliance. The surface settling rate is about the same range, 300 to 1,200 gallons. And there's one additional process control test we can look at, and that's the solids loading rate. And what we're looking for is 12 to 30 pounds of solids per day per square foot of area. So if you look at the pounds of MLS that are going into the clarifier, divided by the area, pounds per day of MLS that are going into the clarifier, divided by the area and square foot, that would let you know, are we between that 12 and 30 pounds of solids per day? And I'll give you an example here of that. Here we have a secondary clarifier. It has a diameter of 72 feet, and it has a flow of 2,900,000 gallons, and the MLS concentration is 2,800 milligrams per liter. So we have to do a pounds formula first of all to see how many pounds per day of MLS that we have. And you notice what I did there. Instead of 2,900,000 gallons per day, I just moved my decimal place to the left 6 spaces, and I called it 2.9 MGD times the 2,800 times 8.34, and we get 67,721 pounds per day of MLSS that's going to the clarifier. And we calculate the area, diameter times 0.785, and we have a total area of 4,069 square feet. We do a simple division here, and we get 16.6 pounds per day per square foot being applied to that clarifier. And that is between 12 and 30 pounds per day per square foot. So we're right in the ballpark. And we're pretty much out of time. And I'm going to leave you with this last poll here. And I'm going to, I'll give you, well, however much time you want. If you're able to calculate this, give a minute or so, and then we'll show the solution. And if Lori has questions for us, we'll answer those. Any questions that I can't answer live today, I can answer in and send it to you by the email. I also want to encourage you, if you have any further questions about your specific plant or about this training, you can email me at gpearson@mtu.edu. Also, I've included a references sheet that have a lot of manuals and additional process control information that'll be good to add to your library.
Thank you, Greg. I'm going to go ahead and I know we're still going to do the Q&A, but I just want to do our wrap up in case some people do have to jump off right at the end. But I just want to thank everybody and on behalf of our team here for joining us and taking time out of your day to join us in this webinar. And I really hope you found it valuable. And if you didn't notice already, I did drop the attendance certification and feedback survey link into the chat. So please do go grab that if you need that certificate of attendance. That is the link that you need. That is the action that we said you need to take if you do need that certificate. But if you have any questions, please feel free to email us at the Center for Technology and Training. And if you need that email, I'm going to drop that into the chat again, just in case. Um, but we do have a couple questions, Greg, and while we're finishing the poll, I will message those to you so you can see them while we're waiting.
All right, for the sake of time, I'm going to start showing the solution to this poll, and then we're going to do our best to answer the questions here and wrap this thing up for the day. So let me just make sure okay, make sure this matches. Okay, good. So we have a circular clarifier that's 60 feet in diameter, and so we're going to do d squared times 0.785 to get the area, and we have a flow of 5,256,000 gallons per day. So we want the overflow rate in gallons per day divided by the square feet. So we simply divide that 5,256,000 gallons. That's supposed to say per day, sorry. Day. And we get 1,860 gallons per day per square foot. And that is right in the ballpark between 300 and 1,200. Now I'm going to go to the questions here. And there was a couple of little slides that you can look at when you get the handout that will be good for you to look at. And I'm going to just go to the bottom here. And look at some of these questions. And the first question here is from Palermo. Thank you for this question here. In conventional aeration, I lost it here. In conventional aeration, continuous flow plants, a lot of the sludge beds of the final clarifiers becomes an unintentional anoxic zone, leading to floating sludge via denitrification. Are there any simple procedural tricks to reduce the likelihood of those beds overturning, or are major plant upgrades the only remedy if it's an ongoing and persistent issue? Um, it may be that I've seen some designs where they followed with a like a final oxidation stage before going into the secondary clarifier. It may be it. I imagine it's possible that you've probably already checked this, but it's possible that some of these types of problems could be due to sludge removal equipment, where there's a little bit of sludge left in the clarifier that's causing the rising sludge. And um, maybe a little bit more if it's continuous, you couldn't do more frequent, it would be continuous, but maybe trying to reduce the sludge blanket down a little bit smaller. That would be my off the top of the head suggestions, but you'd want to check those suggestions with a engineering consultant, that knows your particular plant. But a little smaller sludge blanket might actually help. And from Connor says they're an engineering consultant, and I lost it. The chat box is small. And they're working on a community on constructing a new extended aeration activated sludge plant, an oxidation dish with final clarifiers that will be replacing the existing conventional plant. Um, they're nearing the end of construction. And are there any? I don't know why it's so hard to keep this steady. During the end of construction, we'll be starting up the new treatment process in the coming months. Do you have any recommendations on how to best proceed with starting up this new plant treatment process? Specifically when it comes to managing the sludge in the early stages of the startup and building the proper solids inventory and operation. Yes, that's a good question. I was just reading that about that, and some of the basic techniques, of course, are having a higher recirculation rate at the beginning to maintain that sludge and build it up. And of course I'm sure you probably know more than me about this already, but uh, possibly using some seed sludge from another plant or from the existing wastewater plant to start it up would be um, some basic suggestions. But there some of the resources that I've included in the references document do address plant startup. I hope that's about all I know that I can offer right now. But we do have, if you'd like to explore this further, both of those suggestions, if you send us an email, there's engineers on our staff that have designed plants and started up plants, and we have access to a nationwide network of experts in that area. And I would love to connect you with maybe someone um, who can give you more detailed more detailed answers and guidance for that transition. And that's all I have, Lori.
Yeah, that's a good point. I mean, that's what we do. We connect people too. So if you have a question that we can't answer, we're happy to make those connections. So please do email us if you have questions. We have another question that just came in. This is from Robert. On the primary clarifiers, should you leave the arm running 24 hours a day or turn the arms off for a while?
I've never heard of a situation where you would turn the arm off. As far as I know, they are continuously moving at a slow speed. Um, yeah, I don't have any. Unfortunately, I don't have any advice on that. I what would be the reason, Robert, to turn them off? Why do you turn them off? Just to save energy? Anyway, that's all I have on that. I wish I could wish I had something to go on to add more, but I don't know of any reason to turn them off. There might be, but I don't know about it.
Okay, thank you, Greg. Um, that's all that I have right now for questions. So what we'll do is we'll kind of hang tight just for a couple more minutes in case anybody has any more questions. But thank you again, everybody, for your participation, and I hope you got a lot out of this class. Um, if something comes to you after we close the session, please feel free to email us and let us know. We're happy to answer questions afterwards. Um, and that it inspires us to add more content too, based on your questions. So thank you for that. And please do let us know in the feedback survey if there are other things that you would like us to train on or do differently in these trainings. So it really does matter to us that we look a lot towards those surveys, and it means a lot that you take time to fill it out. So thank you. Um, and thank you, Greg, for your time again. It's always fun to moderate with you. And I think we'll kind of leave the session open for 5 more minutes. And then if it looks like things are kind of quieting down, I'll give you a warning at that last minute that will close the session down. So thanks again, everybody, and have a good night.
I see your comments too, Robert. The